Okay, Bismillahirrahmanirrahim. Okay, in our last part of the video for our second week for under Synchronous Generator, let's discuss a few example. Basically one example, but there are a few part. Okay, so for this example here, we're going to discuss on how to apply the active and reactive power formula that we just derived just now. Okay, so let's take a look at these examples here. So you have there is a 50 MVA, okay, 30 kV, three-phase 60 Hz synchronous generator. Okay, so S here is 30, is 50. Okay, the three-phase power here, and the voltage here 30 kV is a phase-to-phase voltage. All right, and the frequency here is 60 Hz. A synchronous generator with a synchronous reactance of 9 ohm per phase and a negligible resistance. So basically this is the synchronous reactance XS is 9. Okay. So the generator is delivering rated power at 0.8 power factor at the moment and at rated terminal voltage to an infinite bus. Okay. So this is your generator here. Okay. It's applying power at 0.8 power factor. So this is your power factor 0.8. And let's take a look at the first question here. So the first question asks you to find what is the excitation voltage per phase, which is what is E, and its power angle delta. All right. So let's use the formula that we have studied before. So the first thing we need to find is we need to find the voltage and current, and then we need to use this formula here. Okay. So we need to find what is the generator voltage here using this phasor. It's equal to V. The voltage phasor is a constant. And you need to find what is XS and IA. Alright. Ultimately, this is, XS is fine. We know it's 9. And here you want to find. And we know this already. Okay. So let's move on to first step. Basically, we know that the three-phase power is 50 MVA at the angle of cosine 0.8. So 0.8 basically the theta power factor. The cosine of this power factor lah. Okay, so if you do that, you will have the apparent power is 50 MVA at the angle of 36.87 degrees. Okay, so if you split that into P and Q, so this is your P 40 megawatt plus JQ. Okay, so Q, your reactive power is 30 megawatt. So this is Q is basically being delivered since it's a lagging power factor. Okay, remember, if it's lagging power factor, then you have P and Q delivered to the network, and Q is this 30 megawatt. Okay, and then after that you need to find what is the rated per phase voltage. Okay, remember the phase voltage is basically the phase to phase voltage divided by SERT3. Okay, if you divided that, you have 17.32 kV at the angle of 0. Okay, remember we always assume the reference voltage of V phase is always at 0 angle, 0 degrees. Okay. So and then after that, you want to find what is the rated phase armature current. Okay, the IA here, this current IA. Okay, it's just remember from previous example we used this formula before. Is the three-phase apparent power conjugate divided by 3 multiplied by V conjugate. Okay, so S three-phase conjugate is basically 50 at the angle of minus 36.8 degrees. So you see previously is positive, right? Now because you to take the conjugate, the angle become minus, and this time multiplied by 3 is just to change it into kilo from megawatt. Okay, to kilo. Okay, so divided by 3 multiplied by 17.32 at the angle of 0. This is the phase voltage. Okay, and if you divide that, you will have the current will be 962 at the angle of minus 36 degree. See, now you can basically draw the phasor diagram. Like say for example, this is the V phase, and then that will be the current, because you know the angle is minus, right? This is minus 36 degrees, right? 36.87 degrees. So that will be your phasor for IA. Okay, this is the phasor for V phase. All right. So this is the angle. This is basically the angle of between the voltage and current. So and then the excitation voltage, we can use this formula from 3.12, basically from the Hadisada textbook. Okay, you can refer this example from Hadisada textbook that I share with you in OneDrive. Okay, it's the same problem and the same solution. So basically, I'm just explaining to you what are the steps in this problem. Okay, so if you go back to this formula, so E equals to, okay, 1732.5 is basically the voltage here, okay, because angle 0 that doesn't matter, you don't have to put an angle here. Okay, this is the phase voltage V plus J9. What is J9? Is JXS. Okay, this is JXS is 9 ohm, right, per phase, multiplied by the current IA. Current IA is what the current we just calculated just now. Okay, if you multiply that out, and then you will get the voltage, generator voltage, which is basically this voltage as 23,558 kilovolt at the volt at the angle of 70.1 degrees. So if you plot the phasor diagram, it's probably around this magnitude here. Okay, all right. So EAE, so basically perhaps the fact is around here. So this theta, the delta angle here is basically the angle of delta. So basically this is the angle, the 17.1 degrees is the delta. Okay, so and then so let's just say here the excitation voltage per phase. So E here is the generator voltage or excitation voltage, the same thing. So when I say a generator voltage is also equal to excitation voltage. So E generator is equal to excitation voltage. Okay, so the voltage is 23.56 kilovolt at the power angle of 17.1 degrees. Okay, so I hope you understand this part here. Okay, all right. So let's go on to the next part. Okay, for the same system. Okay, so the next question is say that with the excitation held constant, meaning that when you have the E here is equal to constant, meaning that from previous example we know that E is this value here, 23.56. okay, E here is 23.56. okay, at the angle of 17.1 kilovolt. Okay, it's constant. You keep that E. Now our found EA, okay, the driving torque is reduced until the generator is delivering 25 megawatt. We know that, okay, the power of the megawatt can be changed by changing the torque. Driving torque means not the driving, it means the torque from the prime mover. Okay, this torque here, the prime mover is reduced until the generator deliver 25 megawatt. So previously the generator is serving, let's say, how many megawatt there? 40 megawatt, right? Okay, so from 40 megawatt, so from 40 megawatt, the generator torque is reduced until it goes to 25 megawatt. Okay, so what will happen? Okay, so we want to find out what is the armature current, the IA, and the power factor. What's the new power factor? So if we reduce the P, so the original P is from 40 megawatt to a new P, okay, P prime here is 25 megawatt. So what will be the current and what will be the power factor? Okay, so in order to solve this problem here, we can use this formula here, which we derived before. Okay, so this is the relationship between the real power, the watt, and the voltage, the phase voltage or excitation voltage, and the phase voltage, as well as the synchronous reactance and the power angle. Okay, so okay, if you rearrange this formula here, okay, so delta, basically sine delta is equal to P 3 phase multiplied by XS divided by 3 multiplied by E multiplied by V, right? So if you want to find the delta, you just take the inverse sine of this expression here lah, which is basically this one here. Okay, so delta is the inverse sine of, okay, now what is the P? P is now is 25 megawatt. Okay, it's a new power because previously you have 40 megawatt. Now you are trying to reduce the exported power, which is power coming out from the generator, from 40 megawatt to 25 megawatt. So this is a new. Okay, so basically you are looking at the new angle, delta angle here, because previously you have a delta of, let's see, what, 17.1 degrees, right? So what is the new angle? Okay, of course, if you change the power, as I said before, this power, real power here, depend on the voltages and the angle, right? So okay, so basically if you change the power, definitely you will need to change the angle here. So what's the new angle here? So you want to find the new angle for the new operating real power. Okay, so we just use this formula here. All right, so 25, the new power multiplied by 9. 9 is the XS here. XS here. This 25 again is a P new. Okay, 3-phase power divided by 3, divided by 23.56. Okay, 20.56 is the E, the excitation voltage. Remember, we want to maintain that same voltage. Okay, so maintain that same voltage, only the magnitude, not the angle. Okay, so basically the magnitude, like I say that the excitation held, meaning that the magnitude of the voltage, excitation voltage, the magnitude, okay, is held constant. Okay, so and then but multiply by the voltage of the field. Of course, the terminal voltage will always be held constant. Now we don't want to change that phase voltage. Okay, 17.32. So if you plug in all the number, you will, I mean, to take the sine inverse of that value, this value here, you will get around 10.59 degrees. Okay, so from 17.010 degrees, it goes down to 10 degrees. So if you remember the power curve, let me clear this thing up. Okay, remember the power angle characteristic curve. So you have this kind of curve, right? Okay, so this is a 90 degrees. So originally, let's say you are working on 17 degrees, and then if let's say this is a P, this is the delta. Okay, so if you reduce angle to 10 degrees, and then the power originally at this point here, P, and then if you reduce the angle, then you will have a new operating point, P new. Okay, so basically if we reduce the angle, then you need to reduce the angle of the delta, the power angle here. So basically power angle here is the angle of E, the angle of delta, the generated voltage here. Okay, so you just change the power angle of the generator voltage. Okay, and if you change the generator voltage, and then you will get a new megawatt value. All right, so and then after that you already find the new generator the angle, power angle, and then again you want to find the armature current. You use the same formula as previously. So is the new the voltage, the magnitude of the voltage, but now we need to insert a new power angle, delta here. So this is E, because they say E here is constant, right? It's constant from previous example, from part A. And then minus, this is the V, the phasor B, at was 17.32 at equal 0, divided by XS. Okay, all right. So then if you plug in the number, you will get the armature current now is 800 kilo amp at minus 53.43 degrees. Okay, so so now the power factor given here is by cosine. This is so if you know the current phasor here, and then this is the theta power factor. Okay, this is the magnitude of the current, IA magnitude. So and then now the power factor is 0.596. So if we look from previous example, from 0.8 power factor previously, okay, now it has been reduced to 0.596 power factor. Okay, so of course if you reduce the real power, of course it will change the power factor of the system lah. Okay, all right, so let's take a look at the example part 1 also, but on question part C. Okay, now the same system that we had before. Now if the generator is operating at the excitation of part A, okay, what is the steady state maximum power of the machine that can deliver before losing synchronism? Okay, so also find the armature current, which is IA. Here the first one, you want to find the P max, which is 3-phase. Okay, all right, and also you want to find the IA. What is P max and what is IA? Okay, so the solution is that, okay, we know that from this formula here, okay, if we know that the relationship between the power, 3-phase power, and the voltages and the circulators and the powering angle is based on this formula here. So at 90 degrees, we know that this is maximum. Okay, so from previous formula that we know that P3 max Okay, here speed max equal 3 multiplied by EV divided by X, the synchronous reactance. Okay, so we just plug in the the generator voltage is the same voltage, 23.56, okay, kilovolt, and the generator phase voltage is 70.32, and the synchronous reactance doesn't change, it's the same number no matter what, is 9. Okay, and then you get the maximum power of 136 megawatt. Okay, so basically, as you can see here, if you plot again the power angle characteristic curve, okay, so basically at this, if you plot that at 90 degrees, then this generator can safely operate below 136 megawatt. Okay, it cannot operate more than 136. In fact, it cannot even operate even 130 because it's very, very close to this is what they call the static stability limit. So the operator or generator will always try not to operate the generator even close to this region anyway. Maybe around this region only. Okay. All right. So and then after that, you calculated the maximum power of 136, and then the question asks you to find what's the armature current. Okay, again, the armature current for at the maximum angle. So you can see the same formula as before, but now the power angle you set it at 90 degrees because you want to find what is the armature current at maximum power. Okay, so at maximum power, if you plug in this value here, except they change the angle to the maximum power 90 degrees, they will get around 3000 kilo amp, 3248 ampere. Okay, so this is basically the maximum. So the armature current cannot go beyond this IA here, cannot go beyond this 248 ampere, or the generator will face a stability problem and the generator will fall out. The synchronism will not synchronize anymore to the system, and it will basically the generator will be disconnected from the system in order to ensure that the power system is operating in a safe manner. Okay. So again, basically the power factor given is basically the maximum that the generator can operate at 0.8 power factor leading. Okay, so it cannot go beyond that leading power factor. Okay. All right. So okay, this is taking the same example. So this is the same machine, the same generator, the same frequency, the same voltage phase, the same synchronous reactance. Now we have add a few more additional question. Okay, so this is part 2 for the same example A. So this is also from Hadith Adat. So let's just please follow me and how are we going to solve the problem. Okay, so this is the same generator. Okay, so now generator is delivering 40 megawatt initially at terminal voltage 30 kV. Okay, so the problem is to compute the power angle. What is delta? What is armature current? What is the armature current? And what is the power factor? 3 parameter here. Okay, when the field current is adjusted for the following excitation scenario. Okay, so basically what will be these 3 parameter under these 3 different scenario situation here. Okay, first situation is that when the excitation voltage is decreased to 79.2% of the value found in example A part 1. Okay, this is from previously lah. Okay, and then secondly, what is the excitation voltage? What is this delta IA and power factor when the voltage is further decreased to 59.27 degrees. Okay, so A and B is just a matter of different percentage lah, not degrees percentage. Okay, and then finally part C, find the minimum excitation below which the generator will lose synchronism. Okay, you want to find what is the minimum excitation value that we lost synchronism. Okay, so part A first. Okay, so now the excitation voltage, as you can see, if it's reduced 79% meaning that the new excitation voltage is 0.792. This corresponds to 79% approximately, multiplied by this is the generator voltage previously. Okay, the magnitude, and then you will get around 18.657 volt. Okay, so generator has been reduced to that voltage from 23 to 18,000 volt. Okay, so now you want to find what is the power angle armature current, and power factor. Okay, so to find the power angle, we can use this formula here, relationship here, this here. Okay, you just invert that to find the delta. Okay, for here, use the same formula. Okay, so delta is equal to the inverse sine of 40. This 40 here is the P. Okay, sorry, is the P3 phase. Okay, and then 9 here is the XS. Okay, multiplied by 3. Okay, 18.657 is a new voltage here, E. So this is a new voltage, this one here, multiplied by the phase voltage. This is a phase to neutral voltage, 17.32, the same voltage that we had in the same example before. Okay, so now the delta will be at 21.8 degrees. Okay, at 21.8 degrees. So, and then if you want to find the armature current, you can use this formula here. Okay, so your armature current, you can solve for armature current. Okay, do that. Okay, so if you change this formula here, okay, so this is sorry, but this is E. Okay, this is voltage of E, the new voltage at this new angle, 21.8 degrees. Okay, this one 21 degrees minus the V, because it doesn't change. The phase voltage always is assumed constant, and divided by the synchronous reactance. And then you got a current phase armature current of around 769 ampere at the angle of 0 degree. Okay, so and then the power factor is cosine theta, which is 1. Okay, so basically this is when you have a cosine theta is 1. It's basically this machine is operating under unity power factor. Okay, all right. Okay, let's go to the next one. So if the voltage is decreased to 59.2%, okay, let's again do part A, but now we change the excitation voltage is decreased up to 59.2%. So what will happen to the power factor, the angle, and the voltage? Okay, so again, we repeat the same step as before in part A. So E equals to 59% multiplied by 23.6558 volt. And you have the new generator voltage is 13.9 kilovolt. Okay, you repeat the same equation here to find the new angle delta. Okay, you plug in the new number now, except the only difference is this value here, the new generator voltage, our excitation voltage. Okay, excitation voltage is basically E lah. Okay, and then you have a new angle of 29.748 degrees. Okay, and then again, if you after that you want to find the armature current, you use the same formula as before, except now you have a different angle per angle degree, and the armature current will become 962.3 ampere. Okay, so from the phase power angle, from this current here, you can find the power factor, because this is the angle of theta power factor. Okay, so remember, armature current is always the magnitude of the armature current at the angle of theta power factor. Okay, so now because of 36.8 degrees, now so now the machine is operating at 0.8 power factor leading. Okay, because why is leading? Because you see this is a positive number, right? Okay, so remember that V here is always 0. V kan is 0, but now you have an I of A operating this way, right? Because the angle is positive, right? This is theta power factor is positive 36.87 degrees. So the I is in this direction on the complex plane of the phasor diagram. So so definitely this is a leading kind of power factor situation. Okay, all right. So that's answering question on part B. Okay, and finally, let's try to answer part C, where the question asks you to find the minimum excitation voltage E below which the generator will lose synchronism. Okay, remember, when the generator will lose synchronism, the only criteria this basically is when delta equals to 90 degrees. Okay, so if we set delta into 90 degrees, all right, so you plug in the same formula here. You want to find the minimum excitation, so we want to find what is the voltage here, which is 40 megawatt. If you use this formula again, okay, of course, this is the maximum. So when the maximum power, which is sine 90 degrees, is equal to 1, right? Okay, so you just plug in, use these three. So 40 megawatt is the power exporting by this generator, and then multiplied by the synchronous reactance divided by 3, multiplied by the phase voltage multiplied by 1. Okay, all right. So 1 here is basically the power factor. Okay, sorry. 3, 1. Okay. So, and then after that, we find the armature current IA, okay, is using this formula here, okay, this expression here. So, 6.928 kV is this value here at the angle of 90 degrees, okay, because we want to find what will be the armature current when the generator will lose synchronism, which is at that stability limit. Of course, the V is the same, okay, and IA is J9 here, okay. All right. Okay. So after that, if you plunge in the number, you will find the current armature current is around 2000 ampere. Okay, 2073 ampere at the angle of 68.2 degrees. So basically, what we can say that the current phase angle show that the power factor is cosine 68.2, which is 0.37 leading. Okay. So as you can see that this is basically the maximum power factor that maximum power factor limit that the generator can serve. If it's beyond that, if it's higher than that, then it will be a problem lah. Okay, so generator is under-excited and is receiving the active power. Of course, when you are in leading power factor, the Q is being exported. So basically, you have a Q going back into the generator from the system. Right? So it acts like an inductor here. Okay, so basically I have come to the end of the week 2 lecture. So I've shown also a few examples, and I hope you can go back and see all the few videos, 3 or 4 videos that I have posted before. And I'll see you again next week. So next week we're going to go into a new topic, which is on transmission line model. So I hope to see you again next week, inshallah. So if you have any further question, feel free to send me a message through our WhatsApp group, and I see you again, inshallah. Okay, thank you very much, and assalamu alaikum.